there's a little surprise in this presentation because I was about to present to you Alicia Okani, who is a 6-year PhD student at the UC San Diego. And her research is in the intersection of internet measurement and web privacy. And she has also had numerous publications in renowned journals, of course. And she has also been a recipient of the NSF Graduate Research Fellowship and served as the co-president of the University of California, San Diego's Graduate Women in Computing program. But Alicia, unfortunately, due to a scheduling issue, couldn't make it. But we are lucky enough to have found a representative who will be sharing the content of the study that she's been focusing on lately. And specifically, her study is on how local frames are mishandled by a wide range of popular web security and privacy tools. And that basically results in user vulnerability. As a fact, actually, there are techniques that go against exactly the types of things that users try to protect themselves from. And the tools studied are vulnerable in different ways, but all share the same root cause. And which one that is going to be, I will leave that up to Anton to describe.
Yes, so the name of the paper here is Local Frames Exploiting Inherited Origins to Bypass Content Blockers. And Alicia is very kind to put my name there, but I want to be clear, this is all her work, her slides, and this was done with her collaborators, some of which are employees at Brave, and Alex Norand is her PhD advisor. So all credit where credit is due. If there's any mistakes, it's my fault. So just a quick preview of what's going to be in this talk. Basically, there is a systemic vulnerability that Alicia has discovered. And in all of the Adblock tools that she decided to evaluate for vulnerability to this particular thing, all of them were vulnerable in some way. And in fact, this exploit appeared on a lot of different websites across the internet. So it's quite an impactful vulnerability. And those are the tools that were studied under this research. So quick overview of content blockers and their capabilities. I think most of you are probably familiar with this stuff, so we can go pretty quickly. You all know what content blockers are. And then this is like ad blocking, how it works, right? So you can receive content from a remote server. You can receive potentially fingerprinting scripts from a remote server. And if you use an ad blocker, you might want to allow the good content and prevent the bad content. And other capabilities in ad blockers separate from network blocking could be resource replacement, where you're replacing a script with something that is less harmful to the user and located locally so it doesn't have the same privacy concern. Scriptlet injection, where you're customizing the behavior of a page, tweaking how it works, using a polyfill kind of thing provided by your ad blocker. Or cosmetic filtering, where you're hiding parts of the page from view. So next, I will overview what local frames are. So if any of you have done any kind of web development, you might be familiar with iframes. So in this kind of example, we have a page foo.com. On the left, there's a script that's just running in the page context. On the right, we have an iframe, and that iframe is used to gain isolation and sandboxing capability. In this case, the iframe has a source of bar.com, which is a third party when you're evaluating it compared to foo.com. You could also have what's called a first party iframe, where the source would be foo.com. But what if I told you there's actually another type of frame? I'm sure a lot of you don't know about it. And it is called a local frame. And so we actually refer to anything which has a non-network URL as the source as a local frame. And what's commonly used is about blank. You can also sometimes have about src, or just like literally no src specified. And so that is going to be a local frame. There will be literally no content in it. But the nice thing about these is that you can actually fill them using JavaScript So you can insert a script or some HTML into it without ever having to make a network request, unlike the other types of frames. So this is pretty interesting, and they have a special property called inherited origins, which we'll get back to in a moment. And just to clarify, you basically, this is still going to be sandboxed from the rest of the page, but there is still some communication ability between a frame and the host frame. So real quick, what is an origin? It's basically a unique combination of a protocol, hostname, and port. And a lot of times the port you can just ignore because it isn't specified. It's just part of the protocol as well. So if you have an HTTP site and an HTTPS site, those will be definitely different origins. Or if you have two HTTPS sites but with a different host name, those will also be two different origins. And critically, content blockers will often use origins to determine whether or not to block a request or allow a request. So you can see here that if you have a website, shopping.com, which embeds a facebook.com resource, that would be blocked as a third-party request, versus if you have facebook.com making a request to facebook.com from itself, that would be considered a first-party request and would not be blocked if you have a network rule that says it should only apply to third parties. So inherited origins, and this is where we kind of come to the interesting part where nobody in this room knows how they work, apparently. All the so-called Adblock experts, myself included. So what is the origin of about blank? Well, there isn't a protocol, there isn't a host name, there isn't a port, right? It's just kind of this weird, like, special thing, edge case. And as it turns out, local frames are supposed to inherit the origin of their parent frame according to the web spec. And as it also turns out, many content blockers just weren't aware of this fact, and instead they decided to use the frame's URL or something else entirely. So that's pretty interesting. So how does this actually work in practice if, let's say, some site wants to exploit this vulnerability? So Alicia put together a few test pages. This is an example of one used for network blocking. We can see that there is a network request to some benign content on the left, and there is a network request to a fingerprinting script on the bottom. That should normally be blocked by an ad blocker. And so if you wrap that fingerprinting script in a local frame, it should also be blocked. But as it turned out, in a lot of cases, these were not blocked. So that is a very clear vulnerability where simply by wrapping a resource inside of a local frame, you can totally evade a ad block rule designed to specifically block that kind of resource. So Alicia and her team looked at all of these different tools you can see on the left. And across the top, you can see the different capabilities that each of these tools may have. And there are, each square that has a bug is representing one instance of the vulnerability. If there is multiple bugs in a square, that is because that platform has maybe multiple versions. So iOS and Android and desktop would be considered 3 separate bugs for the purpose of this research. And then you can see that literally in every row there is at least one bug. So this is a widespread systemic thing. This is not just like somebody messed up. This is everybody doesn't know what the heck they're doing. If we look even specifically at DuckDuckGo and Safari Content Blocker API, those don't even have all of the capabilities listed here, and they are still vulnerable to this thing. And finally, we will go over 3 different case studies. One of them is going to be Brave Browser on iOS. Then another one is going to be AdGuard. And the last one, or I think it's the other way around. Sorry. The first one will be the Safari one. So the first case study of the Safari Content Blocker API, this is basically if you have developed a browser for iOS, or if you've developed an iOS app with a web view inside of it, and you want to block something in there, or a Safari extension, you're basically forced to use this for ad blocking capabilities. just because that's how Apple's platform works. And as it turns out, cosmetic filtering can be evaded in this thing. But the important thing here is because Apple forces you to use this API, this kind of has a cascading effect where a lot of different apps ended up being vulnerable to this simply because they're forced to use this underlying platform. Next case study, Brave iOS. So probably many of you won't be familiar. We of course are using the Safari Content Blocker API on Brave iOS for network request blocking because we have to. But we actually found a clever way. And I should mention the Safari Content Blocker API is not vulnerable to this in terms of network request blocking specifically. But at Brave, we decided, this Safari Content Blocker API is too limiting, and we would like to provide more protections and capabilities beyond what is provided by this particular API, including some abilities to do resource replacements and other things like that. And so we built in a separate path for asynchronous requests. And this is done using a polyfill in JavaScript in the page context. And as it turns out, this particular code path was vulnerable to the bug. And this is just showing that even though we are literally trying to improve privacy by adding more layers of capabilities and technology here, it turns out that this is also adding attack surface, and because of this particular quirk of the web platform, sometimes mistakes happen there, right? Final case study will be AdGuard. So you can see here, this is a foo.com website, and if you have a frame from bar.com, that is a third-party frame, and then if you have a local frame inside of that bar.com third-party frame, then the inherited origin of that frame should be considered to be bar.com. As it turns out, AdGuard actually did anticipate the fact that local origins are a thing, and they decided to use the top page URL as the inherited origin. Unfortunately, that is not the right choice in this case, and it resulted in the inner local frame as having an inherited origin of foo.com. And this, unfortunately, can also lead to not only evasion but breakage in case a rule was applied that was meant for a different kind of context. So all of these vulnerabilities were disclosed to all affected parties, and then Brave, Apple, AdGuard, and DuckDuckGo finished with all of their patches. And in total, 15 out of the 19 vulnerabilities identified were fixed. And although uBlock Origin Lite wasn't specifically investigated as part of this research, the disclosure to uBlock Origin actually helped them to identify a bypass in there as well. So, okay, this is kind of a weird, niche feature of the web that, maybe it's broken a little bit, but that's probably not too bad, right? So Alicia decided to, just to be sure, measure how exactly prevalent this is on the web, and we'll get into those results now. So the team crawled about 22,000 websites on the Trenko top 1 million, and the purpose was basically to measure who is creating these local frames and how many of them are there on the web, and what is inside of them, what are people using them for. And I guess if you guys want to take a quick guess, now would be the time to do it. There's this feature that is exploitable in a lot of content blockers, and nobody really knows how it works. And, who would be using this kind of thing on the web? If you guessed analytics and advertising companies, you would be very correct, unfortunately. So you can see a lot of these, it's kind of divided into top 15K, 15 to 100K, and 100 to 1 million ranking on the Trenko list. So half of the investigated sites were in the first column, and the rest were in the second two. And yeah, there's a lot of these companies that are doing things that normally we try to block as ad blockers, but unfortunately, that is not always the case if your tools are vulnerable. And so what exactly was in the local frames? As it turns out, 56% of the popular websites overall had some form of local frames, And of those 56%, 62% of them were making requests to trackers that specifically should be blocked by content blockers according to filter lists. That is a lot. And 35% of them were also calling fingerprinting APIs. So these were basically just going undetected for a while until the disclosure led to patches in all of the aforementioned tools. So moving forward, what can we do about this kind of thing, right? This is kind of a big impact, and it would be great to avoid this in the future, right? So one of the problems here is that this is basically just an edge case in the web spec, and it is a pretty old one, but it's one of those examples of you really got to be careful when you're designing how the web works, and make sure that when you're considering a new feature, that it fits in well with the mental model of how everything else on the web works. And you want to try to avoid these kind of foot guns as much as possible, and make sure that developers will have an easier time adapting to the kind of quirky behaviors of things, right? For these tools specifically, I mean, I am certainly open to suggestions. I think it would be great to hear from you guys on what we can do better. But Alicia is suggesting potentially we can have some automated testing, we can have formal verification, perhaps anything else. But yeah, the link to the paper is up there if you're curious. I think it's a great read. And there's also a data set published. So yeah, happy to attempt to answer questions. I think I might be able to answer some. There are some supplemental slides in the back, so that may help. But yeah.
As a browser vendor and working on an engineering team that specifically implement extension APIs to run scripts and things in the right context, this is not surprise to me, the fact that it exists. One thing that could affect this problem is that if an extension declares that it wants to run everywhere, it runs on every website except these blank frames. It's available but on opt-in basis. Do you know whether this problem was caused by not booking into this feature?
Yeah, I'm not familiar exactly with that part. So yeah. Yeah, I think I believe that is a separate thing. So I mean, maybe you can find something in the paper if you're interested. But I think this was specifically looking at how local frames are impacting content blockers specifically, and not extension permissions.
Right. Because network requests, they get information, the web request and DNR both get information where the request came from, the initiator. So that information is available to Adblocker if they want to do some type of initiator-based filtering. Yes, a full cosmetic filtering that runs inside the page. I can see two ways to break it.
Yeah.
One by not running the script at all, and two by using the wrong information through try to terminate that by filter.
Yeah, exactly.
So the origin of the iframe, the lookalike frame, is not necessarily going to be the parent, it's going to be the initiator. And so you can actually have it be the origin of, for instance, the grandparent for great grandparent, or even one that's potentially somewhere else. Do you know if any of the patches that the ad blockers or content filters submitted ended up actually causing new exploits because then they assumed it was the parent rather than the initiator?
Is it possible for the initiator to be a separate origin than the parent frame?
Yes.
Interesting.
So if you have a.com embedding b.com embedding c.com, and that embeds the local frame, by default, the local frame's initiator origin is going to be c.com because that's the immediate parent. But what you can actually do is you can do from a.com, you can reach into b.com and c.com through frames and navigate it. You don't actually need to have that be same order. And so then you can make that origin, again, be a.com or b.com through that.
Interesting. So yeah, personally, I have worked on some of the patches for Brave, and I can tell you that we were previously looking at like window.location.hostname or whatever, which is definitely wrong. But I think we switched it to using window.origin in those particular cases, so I hope that is the correct one. according to what you're saying.
Yeah, widget origin would work in a blank.
Yeah.
From the definition of local frames here, as well as anything that doesn't fit the network, which would include data frames, data URLs, and those have a null for it. So that was one of the other questions.
Okay, well, let's talk for sure. And also, I will point you guys to Alicia in the Slack channel. She's there if you have other questions as well. But we can continue.
Thank you for the talk. Say thanks to Alicia, please.
Yes.
I can answer a couple of questions that were asked. So Rob asked if the issue was because we need to specify much about blank, right, in the list of permissions, and I don't remember exactly, but I think that a couple of the issues was exactly because of that. So because it's not really clear, and the same thing goes, by the way, with src doc as well. So you also need to specify much src doc, something like that. Am I right?
Metropolitan as fallback.
Yeah, something like that. I don't remember the exact the exact name that was also mentioned. And to answer Devlin's question about whether what kind of bypass it allows, I think the most problematic part was that when you incorrectly detect the origin, the rules that are supposed to block only third-party requests stop working because the request looks like it's like a first party, or nope, that's just direct request. That was the main issue with trackers and with trackers bypassing because of this vulnerability.
Yep.
Like that. And now it's not that important whether we correctly detect the origin. It's important that now we at least detect it. It doesn't look like some random request without an origin.
Yeah. Although in some cases you could have a rule where you are specifying a specific domain as the source, right?
Thank you. Yeah, this is really interesting work. I think I probably have to dig more into the details in the paper, but I think one interesting thing that I learned from like common filter lists, community lists, is that notion of third-partiness is tied to the initiator, I think, as discussed before, which allows this kind of wrapping of origins, which maybe this exploit is using. This was also like when Dr. Gill was doing MP3, this is a bit of an issue because we use the top level as the party list. We're judging it based on that, and that's something that didn't exist in DNR for a long time, which is now just been added. It's mentioned in the talk yesterday. So I wonder if that's also a helpful path to, but maybe we can adjust those kind of assumptions about what partiness we measure. Are we checking against these filter?
Yeah, exactly. Yeah, I think part of the issue too is like when you're writing a network rule in Adblock syntax, like there is a first party modifier, there is a third party modifier, there isn't like a local modifier, so you don't even think about it, right? So I think as much as we can bake these assumptions into the tools that we're using, rather than just having them be explicit, I think that's good.
Yeah, this is definitely a very interesting and exciting part of the web platform. Like, yeah, so like what I spent some like if you have like a JavaScript colon URL, that's also like a local. But then if you set document domain inside, it changes. Anyway, so what I wanted to say is that a little bit referring to what Sam said. I think there is an assumption there that the depending on the like how it was defined in the initial filter list, like I might be wrong, but I think like for DuckDuckGo, like because how we do generate the filter lists, I think we are actually assuming that we're gonna compare against the actual top level, like what you see in the address bar. So we and then we block based on that. So in this sense, like if you have like a nested a.com and local b.com and then again a.com, that wouldn't be like a third party according to our block list, and it shouldn't be, and that's why. And yeah, we do need to dig into the details of the paper because so much is unclear, and I think it's not like one-to-one comparison in this case.
Yeah, exactly. So actually, if I can get the slides back, there was a supplemental slide about kind of this thing exactly, because in the Safari Content Blocker API, they kind of made this assumption as well that it's solely based on the top frame. And then almost there. Yes, here we go. Yeah, so basically Safari had interpreted it as the third-party iframe is treated directly based on the top-level URL, and so the implication there is that if you design your filter list specifically for this system, you can't necessarily translate it directly to another platform, right? So that is another reason it's important to make sure we have a very clear definition of what exactly is going on in the web spec and how we're interpreting all of that.
So you mentioned using self.origin to determine the origin of a document.
Yeah.
If iframe or document is sandbox with CSV sandbox, that will be null. In Web Exchange Community Group, we have a specification that describes the algorithm how to get the URL for a given document. So maybe you would be interested in.
Yeah, I think that would be extremely helpful.
Yeah.
Yeah.
We're good? Okay. Then thank you, Anton, on behalf of Alicia, I guess.